I'm going to talk to you today about fields, index tokens, and you. And if that doesn't tell you anything, I'll be talking about Lispy. And just the usual forward-looking statements. Anything I say is a lie. These aren't my slides, so we'll be fine. Why are you all here? You're here because you want to make your searches run super fast. You want to take load off your indexers. You want to let other people enjoy Splunk too. You want to get as many searches into your infrastructure without buying any more servers. And whenever you see such a big disparity at the bottom, a couple events you want to look at, say 5 and 171,000 events Splunk has to load off disk. If you see searches like that, you're in the right talk. So these we want to bust. A couple words about me. I'm Martin, I'm from Germany. I work for Consist, a Splunk partner. I'm doing PS consulting. I've been Splunking since 2012, been a trustee since 2014. So you can join me on Answers, join me on Slack, help other people, be nice to each other. So for our agenda, I want to talk to you about how Splunk will turn your log file into index tokens, so how stuff is indexed on disk. And I want to show you how searches make use of that index. And in detail, we will look at breakers and segmentations, what happens when data is being ingested. We want to look at Lispy, which is the expression language hidden behind your generating searches. And we want to look at fields, because fields really power your searches. So breakers and segmentations. Whenever you have a log file like this at the bottom, this is the beginning of an Apache Access log file, so quite a common thing. Awesome, please turn off your mobile phones. Whenever Splunk reads that, there are two passes Splunk makes over that data. One is for major breakers, which is stuff like spaces, double quotes, line breaks, parentheses, all that stuff. And the second pass is for minor breakers like slashes, dots, anything that's considered a kind of punctuation, but not that important one. And these two are the index tokens Splunk will generate. So the big whole token for the entire IP will be an index token stored in the index, and each individual octet will be an index token. So first you go through the major breakers, which will give you the big IP, and then you'll split that big token again by the minor breakers, in this case, the dots. And you can inspect that index. TSIDX time series index is how Splunk stores that index. There's a command line tool called walklex, which you can call. These slides are available for download afterwards, so you don't have to write all that command down. You can download it and then run it yourself on the indexers, of course. And in there, every token you have extracted from the event, or rather Splunk has extracted from the event, is a pointer at that raw event. So whenever you're searching for the word 2016, for example, Splunk will grab that event directly out of the data instead of just scanning all the raw data. Since 7.3, walklex has been pulled up into the search UI. So there's up there it says undocumented. It's been documented for a couple of weeks now. The docs team is still working on it. There's a search command called walklex you can call, and it will then show you what index tokens and what index fields exist in your data, which is pretty awesome because you don't have to have access to your indexers. You don't have to sign into the shell, run a command yourself. You don't have to be an admin to use this command, which is pretty awesome for all the power users in here. And I'll always switch between demos and the slides. So when we run walklex, you can hopefully read it in the back. Quick feedback. Awesome. When you run walklex, there are 3 options you can use. One of these is the first time ever where you can ask Splunk what indexed fields exist in your data. First time ever. So far, it was never possible, but now you can ask Splunk. And these searches run really, really fast. So just start up, and it's done. Over all time on my entire laptop, which is pretty good. So now we know how that data is chopped up and stored. For the next topic, how do we retrieve it? Because Splunk is all about searching. For retrieval, Splunk has made up its own expression language called Lispy, which you don't really see in the UI. It's being generated from your search in the background, and then it's being used to find data in the index and then retrieve those matching events. Whenever you see that square bracket notation somewhere in Splunk, that's Lispy. Another good indicator is the prefix operators. So you won't see the and between different portions of the Lispy, but instead it's pulled out the beginning. And what Splunk does is it takes that expression, it sees which events match that expression, and only those are read off disk, unzipped, field extracted, and then put into your search pipeline. So the more specific your Lispy is, the faster your searches will be. To see what's going on, there's an awesome tool called the Job Inspector, which will not only tell you what parts of your search took how long, but it can also tell you what the Lispy expression is. To do that, you have to enable a tiny debug setting in limits.conf. So you may probably only want to do that on development instances. But if you do that, you get a lovely output at the top. And just to quickly show you, if we run a search for a text like this, the job inspector is down here in the job menu, inspect job. And it will, if you have the debug setting turned on, give you the Lispy right at the top of the job inspector. If your admins don't want to turn that on, there's a search log file which you can open and search for Lispy, which will give you the Lispy in the search log. So your admins don't have to change settings. You can still find the Lispy, but it's a couple more clicks to do. Whenever you want to gauge how efficient your Lispy is, there are two measures you can look at. There's a field in the job inspector called event count. That's the number of events your search really needed. And there's scan count. That's the number of events your search had to load off disk. Ideally, these would be identical. And if event count is much smaller than scan count, then your Lispy is not very efficient. It's loading way too many events off disk. If you're an admin, you can use that search, which I won't go through. Just grab it from the slides afterwards to find searches that are not efficient in terms of Lispy performance. So how does Splunk build the Lispy for a search? It will treat every breaker, whether minor or major, as a major breaker in your search. So when you're searching for, say, an IP, it will not search for the entire token. Instead, it will search for the conjunction of every octet. So it will search for events that contain a 0, that contain a 1, and that contain a 127. Any event that contains these three tokens will be read off disk, and in a second filter, Splunk will check if the entire IP actually exists in the data. And this is fairly efficient, but there will be some false positives. Some data will contain a 1, a 0, and a 127, but won't contain that localhost IP. If you have and or in your search, these are put into Lispy as you would expect. If you or two words, they will be put into Lispy as an or word 1 or word 2. Pretty nice. What happens if you negate stuff? If you're looking for individual words, let's say not bad, that's pretty easy for Lispy. because Splunk can go into the index, it can look for any event that doesn't contain that word and load those events off disk. But what if you have a more complex search? Let's say you're not looking for localhost. This might be the naive approach. You take the positive filter for the localhost and you negate it. Sounds pretty nice, but that doesn't work. Because if you look at those 3 sample events on the right, all 3 of them have a 0, have a 1, and have a 127. But we only want to exclude the very first one. So that approach doesn't work because it would exclude all 3. Instead, Splunk has to load everything. Whenever you see a square bracket, an and a closing square bracket, Splunk will load everything in your index, will load every event, unzip it, do all the field extraction. So whenever you see that, it's pretty inefficient. What about wildcards? If you have tailing wildcards, you may have observed that your searches are pretty fast. Because if you think of the index as a tree, Splunk can start traversing from the root, and at some point it will find your wildcard and then only look at that tiny subtree. But if you have a leading wildcard, Splunk has no idea where to start. So whenever you have a leading wildcard, Splunk has to load everything again. So whenever you have wildcards in the beginning, that's going to be pretty slow. And to show you how slow, I will quickly drop into a demo. You see I'm searching for an IP with a wildcard in the middle. That search went pretty fast. And to be sure, let's look at the event count and scan count, which are hidden in the bottom down here. Our event count is about 12K, and our scan count is also about 12K. So we're pretty efficient, which is fine. But what if we have a wildcard like we're looking for an admin user, but for some reason we forgot the A? And you can see those 2 numbers below the search bar. The second one, scan count, is growing much faster than the event count. So we're loading way too many events off disk here. Wildcards are even more tricky than just performance. Because what happens if you have a wildcard in the middle of your search? Like you have a hello world, and for some reason you put the wildcard in the space where the space used to live. What Lisp will do is it will look for a single token that starts with hello and that ends with world. But if your event contains hello space world, that big token does not exist. So you will not only have slow searches with wildcards, but you can also have incorrect searches. So if we go back to our IP, and you notice the number of events, oh, there's a space missing. If you notice the number of events, we have about 11.9K matching. If I now remove stuff from here, naively you would expect to get the same number of results, but you don't. We will see a significantly different set of events, just 2.3K, because Splunk is looking for a single token 127, and it's looking for a token that starts with a 0 and ends with a 1. And if we check back on our Lisp, we can see that is exactly what Splunk is doing. And when we grab a sample event, let's say this one, somewhere in here there's a token that happens to start with a 1, starts with a 0, sorry, and happens to end with a 1, and that also contains this IP. So it's a by chance hit in your data. And whenever you have wildcards in the middle, a recent version of Splunk will also give you a warning up here. Will give you a warning up here where it says you have a wildcard in the middle of the string. So you have to be careful. It might not lead to events that you were expecting. It might lead to fewer hits. It gets even worse if you have strings like this, let's say Java exceptions. These are indexed as 4 individual index tokens, Java, lang, null pointer exception, and the big one, java.lang.null pointer exception. And these 2 variants will be fine. If you replace the .lang dot with a wildcard, Splunk will find your events based on the big token. If you keep those 2 dots in there, Splunk will look for Java and lang. It won't be efficient because of the leading wildcard, but at least it will match. But if you keep replacing the dot, suddenly Splunk will look for a token that starts with lang and ends with exception. That token doesn't exist in the index. So be very careful whenever you have wildcards that don't live at the end of your word. If you're looking for admin and replace the end with a wildcard, it's fine. There's an interesting construct you can use in search called term, where you can force Splunk to treat the string you're putting inside the parenthesis as a single index token. And to show you the impact, let's say I am looking for this not quite localhost IP. If I search for it using term, it's really fast, because what happens is the Lisp will look for the entire IP. And as we can see, we haven't scanned any event we don't really need. For contrast, let's remove the term. What now happens is it will look for a 0, a 1, and a 127, which matches every local host and maybe some more events. And it's searching and searching and searching. Found the same events, but it has scanned 100K instead of 100 roughly. So it's a 1000x improvement. Sounds great. This also works with t-stats. It's the only way you can make t-stats use what Splunk considers an inexact query. Whenever you get a warning around inexact queries from t-stats, try using term. If you're familiar with case, case tells the search to treat something as case sensitive. Lisp doesn't care about case. So case won't change your search performance, but it might change what events you're looking for. If you're looking for a capitalized admin, use case. There's an interesting approach you can take and combine term with walklegs. For some reason, this approach is much faster than letting Splunk crawl the index. So far, no engineer of Splunk could explain to me why they don't do that right away. I don't know. Trouble with that, walklegs doesn't work with hot buckets. So for recent data, this may not be correct. So don't blame me if it doesn't work for you. But it's fast. Who cares about correctness, right? As long as it's fast. Okay, so far, we've only searched for strings. We haven't used fields. Let's change that. There are 2 types of fields in Splunk. There's search time fields and index time fields. You're probably familiar with both. Just a quick recap, search time fields are really flexible because you can change a field and it will apply to all your data, no matter how long it's been sitting in Splunk. It's really flexible, but in some cases, it's not that fast. We will look at a couple of those cases in a minute. And for index time fields, if you want to recap how they're created, I've put up the standards you need to change in here. They're stored at ingest time. So if you change your extraction, it won't be applied to old data. You lose all the flexibility of search time fields. But in some cases, index time fields are much faster. So it depends on whether you want to get flexibility or whether you want to get ultimate performance, which one is the best case for your scenario. My default answer, it depends. I'll skip that configuration. You can read it up on your own time. Whenever you want to do normalization, let's say common information model normalization for enterprise security or any related use case, a common thing people use is calculated fields. It's an eval expression that lives inside your configuration, inside props.conf, and it's applied every time you search an event from that particular stanza, usually a source type, will run that eval and then give you that result back. Prior to 7.3, these were really slow because in terms of Lispy, that eval is a black box. Lispy can't look inside, it can't predict, guess what the result will be. And whenever you search for a calculated field, the Lispy will look something like this and it will load all your events. Based on the headline, you can guess that 7.3 is a bit smarter, 8.0 as well. And what Splunk 7.3 will do, it will optimize these three variants. It will optimize simple strings. So if you have a field like vendor or vendor product that's set to Cisco, Palo Alto, whatever, and you search for something else, Splunk will be smart enough to look at all that data. If you have a coalesce that picks out the first non-null field of the parameters, that's also fast. And if you have an if in there, that's also fast. Some of you may wonder, what about case? Because case and if are basically the same thing. For some reason, case is not covered. I can't tell you why. And to show you the impact, I have defined 3 fields in my Splunk. One using case, one using coalesce, and one using if. They're all doing the same thing. In case there's no value for log level, it will fill in unknown, which is a common thing you do with SIM normalization. And when we search for the case variant, you can see there's a huge disparity up here. So the Lispy can't be efficient. And you see it's loading everything from all internal indexes. No warn in there. And it's still running while I was talking. If I use the if variant, it's slightly faster. If I use the coalesce variant, it again is slightly faster than the case. And if we look at our Lispy, we can see that the warn has made it to Lispy. So Splunk is only retrieving events off disk that contain the token warn, which is only a small fraction. And to prove that it's not a caching issue, this is slow. We'll let it finish on its own time. By now, 8.0 is out. I didn't find any 8.0 specific changes to how Lispy is translated. Maybe you will. If you do, let me know. Okay, your search might be looking for something that's not a specific string, but it might be looking for something that's, let's say, greater or equal than 500. In access logs again, anything 500 or greater is a server error, which your server admins might be very interested in. What can Splunk do if you're searching for status greater or equals 500? What list of numbers is greater than 500? An infinite list. So Splunk can't do anything, it has to load all data off disk. There are a couple ways to solve that. One way, you can have a lookup of all known HTTP status codes. Luckily, the Common Information Model app already comes with that lookup, so you can make use of that. You could have an index time field, because index time fields are able to do comparisons at the index level. The index knows what values are ingested, so that infinite number problem doesn't exist. A couple of non-solutions. You can try wildcards. You could do status equals 5 asterisk, which will be slightly better, but it will load every event off disk that contains a number that starts with 5. And let's say it's May 5th. all your timestamps might contain a 5. So depending on what day of the year it is, it might be faster or slower. So it's not really a solution. In case of 200 status codes, there's a really bad solution, which is 2 wildcard. Every single timestamp for the next 920-ish years will match. So there's nothing Splunk can do here except spend more cycles. If you have a timestamp like the one at the bottom, for example, in Windows event logs for Defender, there's a timestamp going down to the nanosecond without any major breaker between them. So every event has a unique token in the index, which the 2 asterisks will have to look at and see, okay, this matches, without being any optimization for us. So that is really slow. And if you're in the job inspector, search.index will tell you how much time Splunk has spent on the index. And I will show you that demo just in a second. When we look at the performance histogram in here, you can see we've spent some time processing the calculated fields. We've spent very little time crawling the index, because this was the case example, which doesn't make use of Lispy. We spent a lot of time doing key value extraction for all the data we've loaded off disk, and then done the extraction to then filter the field. So we're wasting lots and lots of time. So we've looked at negations for simple strings. Those were pretty tricky already, but negations combined with fields are even more tricky. Because if you recall, not bad was pretty fine, but what if we search for not field equals bad? What can Splunk do? If you exclude all events that contain the word bad, you've excluded way too many events. Because your data might look like this. It could have your field set to good, but a different field set to bad. So you can't exclude that event using Lispy, even though you don't want to load it off disk. So whenever you have negated fields, Splunk will again load everything. And the impact can be quite severe. So I'm looking for the extracted log level, not the one where I've made the calculated fields, and I'm excluding all the info ones. So I'm only looking for warning, errors, fatal, whatever. And you can see I've got 150K matches, and I looked at about 1 million. If Splunk were to exclude that string, if we manually build that incorrect approach, it will be much faster, which is great. But once it finishes, we've suddenly lost half our events, because some of the events that have a log level of error or warn might have the string info somewhere down that event, and we can't exclude them, which is why Splunk doesn't make that incorrect optimization. So another tricky thing, if you're searching for values that are not really unique to your field. Worst case scenario, if you have a Linux user ID, this happened to me in real life, which happened to be the year you're in, and you search for that user ID, it will find every single timestamp. So there's nothing Splunk can really do if you're searching for something that looks like a timestamp. Any small integers up to 4 digits are usually really troublesome. Again, common offenders, true, false, yes, no, small numbers. Error, again, is a common one. I've often seen developers build log level equals info events that happen to contain the string error somewhere down the message. And if we're searching for log level equals error, we have to load all of those off disk. In this particular case, we can solve it with term, because you all remember the string of segmenters, right? Equals is a minor segmenter. So there will be a big token index UID equals 2019. So we can use term to work around that issue. But, there's always a but, if your data happen to be UID equals double quote 2019 double quote. You all remember that double quotes are major breakers. So that big token suddenly doesn't exist anymore. Big downside of term, you have to know the physical structure of your events, which kind of goes against what Splunk is about. So always be careful with term. You have to know what your events look like as a raw string. It's not using the fields you're extracting. You gain performance, you lose flexibility. It's the usual trade-off most of the time. Another troublesome thing you can do with fields, you can extract a field from a bigger token. A lady actually walked up to me at Ask the Experts yesterday who had that particular problem. For some reason, Rich told her to come to me. I don't know why. If you're familiar with European banking numbers, this is an IBAN. It's a country code, it's a checksum, it's a bank routing number, and it's an account number, all put into one big string. And you might want to extract the country code. So you can search for any IBAN that's German, country equals DE. Sounds simple, right? Right. But what can Splunk do if you extract that using a regex like this? If you search for country equals DE, Splunk will look for a single index token DE. That index token doesn't exist in your data, so you won't find your events. You could either manually fix that. You could search for country equals DE wildcard. You know all the country codes are 2-letter, so you won't find any incorrect results. But you as the searcher have to do the work. That's annoying. As an admin, you could fix that in fields.conf. You could tell Splunk, always append a wildcard to searches using that field. Which is great because the searcher doesn't have to make that work, doesn't have to have that knowledge. But the downside, fields.conf is not scoped to a source type. So this will apply to every single field that happened to be called country on your entire search set. So if you do that, don't call the field country. Give it a name like IBAN_country. Because then you're pretty sure you won't have any accidental hits to a different field that happen to have the same name. Continuing down the string, there's a checksum. For some reason, people might want to search for checksums. You can't append a single wildcard because the string doesn't start with 44. The DE example would at least be fast-ish. It will find any IBAN that starts with DE. In this case, we can tell fields.conf append 2 wildcards, or rather prepend one and append another. But you recall, anytime you have a leading wildcard, Splunk has to load everything. So while you can solve it for correctness, you can't solve this for speed with search time fields. If you need that, consider doing these as index time extractions. Great thing is that format is pretty static, so losing the flexibility is not that big of an issue. So far, I've only talked about regular traditional searches. You're going to the search bar, type in some strings, type in some field filters, but you might be using data model accelerations. If you're in ES or any more well-built application, you might have accelerations down there. Great thing about accelerations, they will pre-build all the fields in the data model as an ad hoc index time field, so to speak. So all those downsides we've had about non-unique values, for example, like small integers, all those are gone if you use data model acceleration. There's always a but, or a however. If the search building your data model or report acceleration is highly inefficient in terms of its Lispy performance, the building of that acceleration will eat up a lot of time on your server. So if you at least make those searches more efficient, you'll get more out of your hardware. The users won't really notice, but you might have to add a couple less indexers, which is good, saves money. And if you're using tstats and don't set summaries only to true, you might know that the last couple minutes down up to now are always loaded ad hoc. They're not accelerated yet. So if the stuff building your data model is really efficient, then those few minutes will also load faster. All right, let's get to the end. If you only take one thing with you, it's you love your job inspector. Whenever you have a search that feels slow, what do you fix? Maybe you have an idea, maybe you don't. Look at the job inspector, it will tell you which part of your search, which aspect is taking up a lot of time. Because if you want to optimize stuff, focus on what is taking up the most time. Don't focus on what is fast already. If you take away two things, it will be the job inspector and Lispy. Because in many cases, inefficient Lispy is the #1 reason for slow searches. And when you look at searches, there's a couple things you always have to be careful about. It's wildcards, small numbers, and of course strings like true, false, and stuff like that, and negations. And if you're a knowledge manager, be careful around calculated fields. First, make sure you upgrade to 7.3 or 8.0 if you're quite brave. Well, it's been released yesterday, so maybe not the best time to do it in production, but at some point 8.0 will be fine. And if you're a knowledge manager building calculated fields, be sure you use if, not case. At least for now, until case is implemented in a fast way. Because why not make use of that optimization? And when you're building searches, always pay attention to the two tiny numbers while the search is running. Because those will tell you ad hoc how fast your search is. And to finalize, I will quickly show you a final demo. Going from bad to better to good. If you recall those comparisons, I'm being as stupid as possible. I'm looking at lots of indexes. I'm not filtering by a source type. So I'm looking at stuff that doesn't even have a status. And I'm telling Splunk, give me anything greater or equal 400. It's running, it's running, it's running. This feels bad. And we can improve that. One improvement would be to get rid of that greater or equals. So we could use a list of HTTP status codes and only look at those. This is significantly faster than before. And when we look at the Lispy, we see Splunk is using a bunch of numbers to retrieve events. This will still have lots of false positives. We have 100K scan count, but only 1K event count that we actually need. So we can do traditional improvements of our search, specify an index, specify a source type, and it's virtually instant. So we've gone from running before I finish talking to virtually instant, which is pretty good. These are the improvements I want you to do, which will take me to the final slide. Thank you for listening. And if you have questions, we have about 5 minutes left. There are microphones up top, so please queue up so the recording can capture your question. And if you're leaving early, please be quiet while we're doing Q&A. Thank you. Thank you. I see we have questions. You're first at the mic.
Right. In terms of when you looked at the local host IP, how does term compare to putting in a double quotes? Does that make a difference in terms of looking up the tokens?
The double quotes around an IP won't make a difference in terms of Lispy. So whenever you have a string with double quotes, it will still apply all the breakers within the string. Please walk up to the microphone if you have a question.
So, instead of using term, if you use brackets, the circular brackets around the term, what is that doing?
Brackets around term? Could you repeat that?
Yeah, so instead of using term, like you remove the keyword term, just keep the bracket.
Keep the parentheses.
Parentheses, yeah.
Parentheses will tell the search how to group that filter, but it won't affect Lispy. So you can use parentheses to have or and grouped in the correct way, but it won't change how the search is translated in terms of minor and major breakers. So you have to have that term keyword to, so to speak, call the term function, if you think of it as like a programming language.
All right, you may have hit on my answer. I was actually about to ask you if you have specific, like, let's say 10 different indexes that you wanted to check, similar to the query you just ran using the lookup table. Like, what would be an efficient way to go in about that? Because I have one query that just keeps running forever.
Could you repeat the question? I'm sorry.
All right, different indexes. Let's say about 8 or 9 particular indexes that I'm checking for IPs and pulling the IP location to pull the country.
Yeah, if you're looking at several indexes, you can just list them out at the beginning.
Just or, something more?
You could either do index 1 or index 2 and so on, or you could do index in list of values, which is similarly fast, just a different syntax. And the index filter itself doesn't really look at the index structure, because if you're familiar with the way Splunk stores indexes, it's a different directory on disk.
Yeah.
So whenever you have an index filter, it's next to time the fastest thing you can filter.
Okay.
Because you either have to look inside a directory or you don't.
Okay.
It's a really fast decision. So specifying an index is great. And if you look at several indexes, just specify several indexes.
All right, would you consider using term in the IP address range field, or what?
Term is pretty useful for IPs, as long as your raw data has the IP that's not contained in a bigger string. So for example, if you have IP colon port, then IP colon port will be the big token.
I got you. I got you.
So you have to be aware of what your raw data looks like.
Okay. Okay. That makes sense. Thank you.
You're welcome.
How can I get this presentation?
The presentation will be available for download on conf.splunk.com. I'm not quite sure when. Usually it's a week or several after conf. But if you need it now, you can see me after the talk, and I can email you.
Yeah, sure. Thanks.
Do you have any experience of using, like in Splunk Cloud, you've got Smart Store now, and how important is the quality of Lispy given the potential that you're having to pull the buckets from S3? I'm assuming it's still important, but less important. Do you have any experience?
Yeah, Smart Store, as the name implies, is fairly smart about what it has to load off the S3 cache.
Yeah.
So whenever you hit a bucket that's not in the cache on the indexer, it won't always load the entire bucket. It will load fragments of that bucket. Okay. And the more specific your Lispy is, the more efficient that approach will be. And if I recall correctly, the Bloom filters will always live on the cache because they're tiny. So if you have very unique terms in your Lispy and the Bloom filter excludes that bucket already, then you don't even have to load anything off cache. Okay. So anything you make more efficient in Lispy will also make your Smart Store indexers more efficient.
Okay, and the other question I had, am I correct in assuming that the numbers we're looking at in the searches, like the number of records scanned versus returned, that that's not stored in any index for me to go and find out where my inefficient searches are?
That's stored in the audit index.
It is in the audit index.
It's
Wonderful.
the big full screen search I had at the beginning,
yeah,
which you can grab out of the slides afterwards.
Okay.
There are 2 values in the audit index which will tell you scan count and event count.
Awesome.
If you're on a reasonable recent version of Splunk.
Yes. Okay, awesome, thank you.
So if you're searching for multiple IP addresses at the same time, using term, what's the most effective or efficient way to run that search?
You can use term together with or. So you could have term one IP or term another IP and so on.
And you do that all within the square bracket?
Yep. You will have a square bracket or and then the set of IPs and closing square bracket, and it will be really fast.
All right, thank you.
We have 7 more seconds, which I guess won't be enough for a question and an answer, but you can see me outside in the hall for more questions because I don't want to steal time from the next speaker. Thank you.